Welcome to a lesson with Dr. Powell. Let's take a look at an example of a type of function that we can apply in a composition to a matrix function, but on after we do the function. So kind of a post composition. So it's not something that comes after it. If we're thinking about a column interpretation of what a matrix means as a function. So in the column interpretation, the input would be R4, or that would be the domain here, and what's coming out in the codomain is R3 here. And let's suppose that we want to apply a function that takes us to R3 again. And now this function that we want to use is one that is going to be what we call bijective or invertible and surjective, injective and surjective function. Now, and we want it to be a linear transformation. Linear transformations preserve different structure. They preserve vector space structure, addition, and between vectors and scalar multiplication. They have some nice properties here. So a bijective function, which in our case preserves structure, we'll call an isomorphism. If we want to be technical, though, in general, isomorphism simply means that there is a reverse map going back the other way that also preserves the same structure, such that if you compose it both ways, you'll actually get to the identity function. Now, this function that we're going to be talking about, this type, we're going to call an airdrop map. And it does have an inverse. So if we go this way and we go back, we're going to have, in fact, notice what's happening. In fact, this is a description of an example. Basically, we take the vector, the input vector, and what do we do to it? We pick one of the entries and we add a multiple of it to another entry. Now, in reverse, if you just take this and then you add by the opposite multiple, or the negative of the multiple of that guy to that same position, notice that this would undo what I just did, because A is being left alone, and so to go back and forth, this is an additive map, one way and the both, that's scalable. These are linear transformations. It works perfectly fine. We're going to call this an airdrop map. And the way that we're, instead of writing down the actual matrix for this, which would be a 3x3 matrix, we're going to actually just perform the composition or the multiplication of matrices right on this itself without actually writing this down. So basically what we do is think about what the resulting composition would be. The first column of the result is going to be the ultimate destination of E1. So E1 comes in here, it comes to this place, and then what is the image of this? We'll just run this type of map. Now let's run this one exactly. What does this mean? You take this result and you do this to it. In other words, you take this last entry right here, and you're going to subtract 2 times the first guy. And you're going to do that to this vector, and that's going to be the first column. You can do the next one. It's going to be the next column, the next one, next column, next one, next column. We can actually do this to all of these vectors simultaneously at once and get the resulting matrix, which is kind of nice. And we call it a row operation. I'm going to call this an airdrop row operation, because what we're going to do is we're going to see this A, we're going to think of lifting it up. So take all the A's, all these guys, think about lifting them up in the air. So let's take a look at that. Let's lift them up in the air, up here. And while they're up in the air, we're going to do something to them. We're going to get them ready for an airdrop. All right. So how to get them ready for an airdrop? Well, let's suppose, for instance, that we want to make this 0 underneath this 1. So this 1, and see this, let's make this a 0 here. How are we going to do that? Let's multiply this whole row by something, by -2. So we do that up in the air. And so it'll be like -2, -4, -2, -6. We multiply this row by -2. Then we take this and then we airdrop it right there on this row. So when we do that, this -2 and 2 right there become a 0. This -4 and that 1 add together to become a -3. This -2 and that -1 add together to become a -3. And this -6 and that 0 add together to become -6. And the other guys have been left the same. 1, 2, 1, 3, 1, 1, 0, 1. Okay, so we're going to call this is now notice what we have right here. We have a matrix, which is the composition of two matrix functions. This one run first, and then this airdrop bijective operation, which we'll call an isomorphism. It's an isomorphism. It's a linear transformation which preserves structure, and it's invertible. It has a map that goes back and forth, which is a true inverse to this function from R3 to R3. So it's a linear transformation which has an inverse that goes right back the other way, like this. Okay. So, and why would we want to do that? Well, if we want to examine kind of what this is doing on its what this map is doing on its fibers, its fiber structure, and what's going on with it, it's kind of hard to see right now. But if we can simplify this map to view it in a simpler way by doing some operations on it, by doing some isomorphisms after, and even some isomorphisms before, and we'll talk about how to do that in another video, we actually can get some valuable information about this linear transformation, about this map and how it's behaving. Is it taking a whole space and flattening it to a plane, or taking a plane and flattening it to a line, or is it kind of preserving things like a plane to a plane, or space to a space, or something like that? And we can get that information very nicely by performing such operations. These operations are also useful for solving systems of equations and many other things. All right, well, this was just a description of what it means to perform an airdrop map. All right, and we'll see more of these in videos to come. Thanks for watching.